Assalamualaikum and good day to all of you. We have now come to the last topic of chapter 4, 4.5, Cauchy-Euler Equations. A Cauchy-Euler equation is an important linear differential equation because it has direct application to Fourier method in the field of partial differential equations. This equation is named after a French mathematician Cauchy and a Swiss mathematician Euler. A Cauchy-Euler equation is an equation of the following form. This is an nth-order linear differential equation. And notice that this differential equation has variable coefficients. If you look at the first term, this first term involves the nth derivative of y, and the coefficient for the nth derivative of y involve a product of a constant a sub n and a variable x to the power of n. And therefore we say that the nth derivative of y has a variable coefficient. Similarly, for this term, for example, we have the second derivative of y, and the coefficient of the y double prime is a product of a constant a2 with x squared, a variable, and therefore we say that y double prime has a variable coefficient. The Cauchy-Euler equation has a special characteristic. The degree of the coefficient x to the n matches the order of differentiation, the nth derivative of y. Okay, so for example, if you look at this equation, 2x cubed y triple prime minus x squared y double prime plus xy prime plus 4y equals to ln x. This equation has a special characteristic. The degree of x in this case is 3, and the order of differentiation of y is also 3. So 3, 3, they are the same. For the second term, the degree of x is 2, and the order of differentiation is also 2. 2, 2, they are the same. For this part here, the degree of x is 1, and the order of differentiation is 1, 1, 1, they are both the same. And for the last term, there is no degree of x, meaning that the degree of x is equal to 0, and there's no derivative of y, and therefore we notice that these two are the same, 0, 0. So this is an example of a Cauchy-Euler equation which fulfills this characteristic. The degree of the coefficient x to the n matches the order of differentiation, the nth derivative of y. So back to the general form of the Cauchy-Euler equation. So you notice that if this is of degree n, then the order of differentiation is also n. If this is of degree n minus 1, and the order of differentiation is also n minus 1. If this is of degree 2, and the order of differentiation is also 2. Here are more examples of Cauchy-Euler equations. X squared y double prime plus 2xy prime plus y equals to 0. This is a second order homogeneous linear Cauchy-Euler equation. The equation is said to be Cauchy-Euler because it fulfills the characteristic of a Cauchy-Euler equation. If you look at the first term, the degree of x equals to 2 matches with the order of differentiation of y, which is also 2. For the second term, the degree of x is equals to 1 matches with the order of differentiation of y, which is 1. And for the last term, the degree of x is equals to 0, and there's no derivative of y. And so this is a Cauchy-Euler equation, and it is said to be homogeneous because the gx is equals to 0. This example is a third order non-homogeneous linear Cauchy-Euler equation. For the first term, the degree of x is 3, matches with the order of differentiation of y, which is also 3. For the second term, the degree of x is 2, matches with the order of differentiation of y, which is also 2. And for the last term, the degree of x is equal to 0, matches with the order of differentiation of y, which is also 0. Notice that the y prime term is missing because the constant for the coefficient of y prime is said to be 0. And that's the reason why the y prime term is not listed in this equation. Here are some examples of non-Cauchy-Euler equations. Let us try to spot which part of the equation make it to be a non-Cauchy-Euler. In this example, if you look at the first term, the degree of x is 3, but the order of differentiation of y is equal to 2, so these two do not match. 3 is not equal to 2, and therefore this equation is said to be a non-Cauchy-Euler equation. For the second example, which term shows that this equation is a non-Cauchy-Euler equation? For the first term, the degree of x is 3 matches with the order of differentiation of y, which is also 3. For this term here, the degree of x is 2, the order of differentiation of y is also 2. However, if you look at the last term, the degree of x is equals to 1, but the order of differentiation of y is 0. So 1 is not equal to 0, and therefore this equation is not a Cauchy-Euler equation. There are some non-Cauchy-Euler equations that can be transformed to a Cauchy-Euler. Example, xy double prime plus 2y prime equals to e to the power of x. It is very obvious that this is not a Cauchy-Euler because the degree of x for the first term is 1 doesn't match with the order of differentiation of y, which is 2. And similarly here, the degree of x equal to 0 doesn't match with the order of differentiation of y, which is 1. So how to transform this to a Cauchy-Euler? Is it possible to do so? Yes, we can do so by multiplying the whole equation by x. So when we have multiplied the whole equation by x, we'll get the following form: x squared y double prime plus 2xy prime equals x e to the power of x. And if you look at the left side, the degree of x is 2 matches with the order of differentiation of y, which is also 2, and the degree of x is 1 matches with the order of differentiation of y, which is also 1. So this is an example of a non-Cauchy-Euler transformed to a Cauchy-Euler equation simply by multiplying the original equation by x. Our interest now is learning how to solve a Cauchy-Euler equation. For the rest of our discussion, we shall focus on Cauchy-Euler equation where the interval for x is larger than 0. Because if x is less than 0, then the approach to solve the equation will be slightly different. So we shall focus only on Cauchy-Euler equation where the interval is x larger than 0. Second order Cauchy-Euler equations. This is the general form of a second order homogeneous Cauchy-Euler equation. Ax squared y double prime plus bxy prime plus cy equals to 0, where a, b, c are all constants. So what is the solution for this second order homogeneous Cauchy-Euler equation? The solution is in the form of y equals x to the power of m, where m is the root of the equation. So if this y equals x to the m is a solution of this equation, it means that y equals x to the m and its derivatives must satisfy this equation. So if y equals x to the power of m, then y prime will be mx to the m minus 1, and y double prime is m times m minus 1 x to the power of m minus 2. Let us now substitute y prime and y double prime into the Cauchy-Euler equation, and we will obtain the following form: ax squared y double prime plus bxy prime plus cy equals to 0. Notice that in the first term we have a product of x squared with x to the m minus 2, so we need to add these two powers, so we'll get x to the power of 2 plus m minus 2. Similarly, for the second term, we have a product of x with x to the m minus 1, so add the two powers, it becomes x to the power of 1 plus m minus 1. X to the 2 plus m minus 2 gives us x to the power of m. For the second term, x to the power of 1 plus m minus 1 gives x to the power of m. And now in this equation, notice that x to the power of m is a common factor. Factor x to the power of m, leaving this expression inside the bracket, 8m times m minus 1 plus bm plus c. So now we have a product of two factors equal to 0, meaning one of these has to be equal to 0 or both are equal to 0. However, we know very well that x to the power of m is never 0. Therefore, for this equation to be true, this expression am times m minus 1 plus bm plus c has to be equal to 0. If we open up the bracket, we'll get the following form: am squared plus b minus a times m plus c equal to 0. This equation is referred to as the auxiliary equation for the second order homogeneous Cauchy-Euler equation. The auxiliary equation for the second order Cauchy-Euler equation is of second degree, and therefore it has two roots. The roots may be distinct and real, or repeated real, or they may be conjugate complex. For the first case, when the roots are distinct and real, m1 is not equal to m2, and the solutions are written as follows: y1 is x to the power of m1 and y2 is x to the power of m2. So these are the form of the solutions y1 and y2 in the case of distinct real roots. For repeated real roots where m1 is equals to m2, y1 is equals to x to the power of m1, whereas to get y2, we need to multiply y1 by ln x. That means y2 is x to the m1 multiplied by ln x. For case number 3, where the roots are conjugate complex, m1 is alpha plus I beta and m2 is alpha minus I beta. The form of the solutions are as follows: y1 is x to the alpha cos beta ln x, and y2 is x to the alpha sine beta ln x. So these are the forms of the solutions for y1 and y2 whenever you encounter a problem where the roots are complex conjugate. The second order homogeneous Cauchy-Euler equation has the following form: ax squared y double prime plus bxy prime plus cy equals to 0. Let us now learn how to find the general solution for some Cauchy-Euler equations. Question number 1. X squared y double prime minus 6y equals to 0. Is this the Cauchy-Euler equation? Yes. If you look at the first term, the degree of x is 2, the order of differentiation of y is also 2. And for the second term, the degree of x is equal to 0 and there's no differentiation of y. So this is a Cauchy-Euler equation. To solve this equation, we have to start by forming the auxiliary equation. The auxiliary equation in general is expressed in the form of am squared plus b minus a times m plus c equals to 0. We need to know the values of a, b, and c in order to get the correct form of the auxiliary equation. So to get the values for the a, b, c, we can just refer to the equation given here. A refers to the constant term for the coefficient of y double prime. So in this case, a has to be equals to 1. So a equals to 1. B refers to the constant term for the coefficient of y prime. In this case, b equals to 0. That's why the y prime term is not listed here. And c is the coefficient of the y. In this case, c is negative 6. Substitute these values into the expression for the auxiliary equation. A equals to 1, so you get m squared plus b minus a, so 0 minus 1 is negative 1, so negative 1 multiplied by m, plus c is negative 6. So this is a second degree auxiliary equation, or we say it is a quadratic equation. M squared minus m minus 6 equal to 0. On the left side can be easily factorized. We'll get the form of m plus 2 multiplied by m minus 3 equal to 0. If the first factor is equal to 0, we get the first root, which is negative 2. And if the second factor equal to 0, we get the second root, m2, which is equal to 3. So these two roots are real numbers and they are not equal to one another. So we are getting the case of distinct real roots. m1 is not equal to m2. So to write down the solutions, for the case of distinct real roots, y1 is expressed in the form of x to the power of m1. m1 is equal to negative 2, therefore y1 is x to the negative 2, and y2 is x to the power of m2, but m2 is equal to 3, so y2 is x cubed. The general solution, y equals to c1y1 plus c2y2. Question number 2, x squared y double prime minus 3xy prime plus 4y equal to 0. Since this is also a Cauchy-Euler equation, we can now determine the values for the a, b, and c. A is equals to 1, b is negative 3, and c is equals to 4. Substitute these values a, b, c into the auxiliary equation. So a equals to 1, so get m squared. b minus a, meaning negative 3 minus 1, that gives us negative 4. And c equals to 4. So the corresponding auxiliary equation is m squared minus 4m plus 4 equals to 0. So this left side of the equation can be factorized into the product of m minus 2 times m minus 2. And we solve this equation, we get two roots and they are both equal to 2. So this is a case of repeated real roots. So if m1 equals to 2, then y1 will be written as x to the power of m1, which is x squared. And since m2 is equals to m1, so the rule is that to get y2, we must multiply y1 by ln x. So y1 is x squared, and therefore y2 is x squared ln x. So the general solution is y equals to c1 y1 plus c2 y2. Question number 3, x squared y double prime plus 3xy prime plus 3y equal to 0. Now let us determine the values of a, b, and c. A equals to 1, b equals to 3, and c equals to 3. Substitute a, b, c into the auxiliary equation and we'll get the following form: m squared plus 2m plus 3 equals to 0. The left side cannot be factorized, and therefore we are going to use the quadratic formula to solve this equation. This is the form of the quadratic formula, and notice that in the quadratic formula there are values a, b, c that we have to plug in. The values of the a, b, c will be obtained from this auxiliary equation. Now the a, b, c from the auxiliary equation will not be the same as the a, b, c that we have obtained from the Cauchy-Euler equation. So for the quadratic formula, the a will be equals to 1, b is equals to 2, and c equals to 3. So substitute into the quadratic formula and then you simplify until you get these two roots. m1 is negative 1 plus square root of 2i, and m2 is its conjugate, negative 1 minus square root of 2i. To get y1, we use the formula x to the alpha cos beta ln x. We have to determine the value of alpha and beta from the given roots. So alpha will be the number at the real part, which is negative 1, and beta will be the number at the imaginary part, which is square root of 2. So substitute negative 1 into here, square root of 2 into here, so we get y1 given as x to the negative 1 cos square root of 2 ln x. To get y2, it's very simple. If you know y1, you can easily get y2 by changing cos into sine. So y2 is x to the negative 1 sine square root of 2 ln x. So lastly, we write down the general solution, y equal to c1 y1 plus c2 y2. What about non-homogeneous Cauchy-Euler equation? How do we solve a non-homogeneous Cauchy-Euler equation? For the non-homogeneous Cauchy-Euler equation, its solution can be obtained by employing the method of variation of parameters. Why? Let us look back at the form of the second order Cauchy-Euler equation. Ax squared y double prime plus bxy prime plus cy equals to gx. So if the gx is not equal to 0, then this equation is said to be non-homogeneous. And we have learned before this that the solution for a linear non-homogeneous differential equation is given in general y equals to yc plus yp. So to get the yp, or the particular solution for the non-homogeneous equation, we have already learned two methods. One is by the superposition approach and the other is by the method of variation of parameters. So for the Cauchy-Euler equation, we cannot use the superposition approach because the coefficient of y double prime and y prime are variables. Okay, so since these are variable coefficients, we have to use the method of variation of parameters and not the superposition approach. Question number 4. xy double prime minus 4y prime equals x to the power of 4. If you look at this equation is not a Cauchy-Euler equation, but we can actually transform it to a Cauchy-Euler equation by simply multiplying the whole equation by x. So we get x squared y double prime minus 4xy prime equals x to the power of 5. So this equation now fulfills the characteristic of a Cauchy-Euler equation. We are going to learn how to solve this Cauchy-Euler equation. Now, since this is a non-homogeneous Cauchy-Euler equation, and therefore we have to find two parts, which is the yc and the yp, in order to make up the general solution. So the first part is to find yc, the complementary function, or in other words, the general solution for the associated homogeneous Cauchy-Euler equation. So the associated homogeneous Cauchy-Euler equation will be as follows. You just use the Cauchy-Euler equation, except that the right side now has been replaced by 0. So we get x squared y double prime minus 4xy prime equals to 0. Next, we are going to form the corresponding auxiliary equation. This is the auxiliary equation, and we need to find out the values of the a, b, c. A equals to 1, b is negative 4, and c equals to 0. The y term is missing because the constant c is equals to 0. So if a equals to 1, the first term will be 1m squared, and b minus a is negative 4 minus 1, that gives us negative 5 multiplied by m, and c equal to 0. So this is the equation that we've got, m squared minus 5m equal to 0. M is a common factor, so now we get a product of m with m minus 5 equal to 0. So if m equal to 0, the first root is equal to 0, and if m minus 5 equal to 0, the second root will be 5. So if a case of distinct real roots, m1 equal to 0, m2 equals to 5, so m1 is not equals to m2. And how do you write down the solution? y1 is x to the power of m1, substitute m1 by 0, so x to the power of 0 is 1. So the first solution, y1 equals to 1. And for the second solution, m2 is equals to 5, so y2 will be x to the power of m2, y2 is just x to the power of 5. So let us form the complementary function yc. Yc is c1y1 plus c2y2. So c1 multiplied by y1, y1 is 1, plus c2 multiplied by y2, y2 is x to the power of 5. So this is the form of the complementary function. The next step is to find the particular solution yp for the non-homogeneous Cauchy-Euler equation. And to find yp, we have already discussed that the method used is the method of variation of parameters. I've already taught you how to use the method of variation of parameters in chapter 4.4 part 3. So these are the following steps in applying the method of variation of parameters. The first step is to find the fx. Fx in the method of variation of parameters has the formula equals to gx divided by a2 of x. What is the gx and what is the a2 of x for the Cauchy-Euler equation? So this is the given Cauchy-Euler equation. The gx refers to the function on the right side of the equation, which is x to the 5, divided by a2 of x. a2 of x is the coefficient of y double prime. In this case, it is x squared. So fx is x to the 5 divided by x squared. Simplify, fx is x cubed. After this, we need to form the Wronskian of the two functions that we have found in the yc. In the yc, we have found that y1 is 1 and y2 is x to the power of 5. So you set up a matrix of size 2 by 2. So the first row will contain the functions in the yc, whereas in the second row, we fill up the second row by differentiating each of the functions in the first row. When you differentiate 1, you get 0. Differentiate x to the 5, you get 5x to the 4th. Now evaluate the Wronskian using the formula a times d minus bc. So the Wronskian is just equals to 5x to the power of 4. The next step is to evaluate u1 prime, which has the formula negative y2 fx over w. Okay, now y2 is x to the 5, so negative x to the 5 multiplied by fx. Fx is x cubed divided by w, which is 5x to the power of 4. Simplify, we get u1 prime as negative 1 over 5x to the power of 4. u2 prime has this formula. u2 prime is y1 fx over w, but y1 is equals to 1, and fx is x cubed, w is 5x to the 4th, so u2 prime is 1 over 5x. u1 can be obtained by integrating u1 prime with respect to x. So since u1 prime is 1 over 5x to the power of 4, or negative 1 over 5x to the power of 4, so we evaluate this integral. So we get u1 as negative x to the 5 over 25. Whereas u2 is the integration of u2 prime with respect to x, but u2 prime is 1 over 5x. Okay, so 1 over 5, integration of 1 over x dx, so we get 1 over 5 ln x. Having got u1 and u2, we can now form the particular solution, which has the formula u1y1 plus u2y2, but u1 is negative x to the 5 over 25, multiplied by y1 is 1, plus, now u2 is 1 over 5 ln x, multiplied by y2, which is x to the power of 5. And then you simplify, you open up the bracket, so yp will be negative x to the 5 over 25 plus x to the 5 over 5 ln x. So this is the form of the particular solution that we've got for the Cauchy-Euler equation. Next step is to form the general solution, y equals to yc plus yp, y equal to c1 plus c2 x to the 5, so this is the yc, plus the yp, which is negative x to the 5 over 25 plus x to the 5 over 5 ln x. So this is the general solution, but we can actually simplify the general solution further by doing the following. Notice that for these two terms, x to the 5 is a common factor, so we can factor x to the 5. So if you factor x to the 5 between these two terms, you'll get c2 minus 1 over 25 as the constant multiplied by x to the power 5. Because c2 is a constant, minus 1 over 25 is another constant, so we get a new constant here. So you can label the new constant as another c2 if you want to, or you can even label it as the c3 or whatever label you want to put it. Here I'm calling it again as a c2. Okay, so in other words, we'll be getting the general solution as y equals to c1 plus c2 x to the 5 plus x to the 5 over 5 ln x. Alright, so the general solution can be expressed in this form, or you can simplify it further to get this form. So no matter which one you choose, these two are acceptable as a form of the general solution for the Cauchy-Euler equation. Here's another problem. X squared y double prime minus 3xy prime plus 4y equals to x cubed. So this is a non-homogeneous second order Cauchy-Euler equation. So to solve this, we shall start by finding the yc. To get the yc, we shall change the gx as equals to 0. So now we are getting the associated homogeneous Cauchy-Euler equation. Form the auxiliary equation. A equals to 1, b is negative 3, and c equals to 4. So substitute into this auxiliary equation, we'll get m squared minus 4m plus 4 equals to 0. When we factorize the left side of the equation, you notice that this equation gives the two roots which are real and repeated. So m1 is equals to m2. Since m1 is a real number, y1 is expressed in the form of x to the power of m1 or x squared. And since m2 is repeating m1, so the rule to form the y2 is that y1 must be multiplied by ln x. So since y1 is x squared, therefore y2 will be x squared ln x. So the complementary function yc is expressed in the form of c1 x squared or c1 y1 plus c2 x squared ln x c2 y2. The following step is to find the particular solution for the non-homogeneous Cauchy-Euler equation. So we begin by finding the fx. Let us recall the given Cauchy-Euler equation. So fx is gx divided by a2 of x, which is x cubed divided by x squared. So when you simplify, we get fx as equals to x. After this, we are going to evaluate w, the Wronskian of the two functions that we have determined in the yc. So y1 is x squared and y2 is x squared ln x. To get the entries in the second row, we need to differentiate each of the function in the first row. So differentiate x squared is simply 2x. To differentiate x squared ln x, we have to apply the product rule of differentiation. So u v prime plus v u prime. So x squared multiplied by 1 over x. So u v prime plus v is ln x multiplied by u prime, which is 2x. We can now simplify this expression. X squared multiplied by 1 over x is simply x. And this part here, we just have to rearrange the order of the product of these two functions. So bring 2x to the front of ln x. So we get the following form. So this is the determinant of the matrix that we have already set up, and now we're going to evaluate the Wronskian using the formula A times D minus B times C. So the end result is W equals to X cubed. For the U1 prime, it is given by the formula negative y2 fx over w. So negative, now y2 is x squared ln x, multiplied by fx is x, and the w is x cubed. Okay, now simplify this expression, we'll get negative ln x as the answer for the U1 prime. For the U2 prime, the formula is y1 fx over w. Now y1 is x squared, multiplied by fx is x divided by x cubed. So U2 prime is just the number 1. Next, we are going to evaluate U1. U1 is just the integration of U1 prime with respect to x. But we know that U1 prime is negative ln x. And so in order to evaluate this integral, we have to apply integration by parts. Okay, so where we let u equals to ln x and the dv equal to dx, differentiate ln x to get du, the answer is 1 over x dx, and integrate dx to get v, and the answer is just x. So apply the formula u times v, so u times v will be x multiplied by ln x minus integration of v du, so x multiplied by 1 over x dx. So simplify this, we get the integration of ln x as x ln x minus x. So substitute into this part here, minus, we still maintain the minus sign, and integration of ln x with respect to x is x ln x minus x, which is got it from here. Okay, now multiply each of these in the bracket with negative 1, so the answer will be x minus x ln x. The evaluation of U2 is very simple because U2 prime is just number 1. So when you integrate 1 with respect to x, the answer is simply x. The last step is to form the YP, which is U1 Y1 plus U2 Y2. And therefore U1 is equals to x minus x ln x multiplied by Y1, which is x squared. Whereas U2 is x multiplied by Y2. Y2 is x squared ln x. Open up the bracket, so at the end we get the answer as just x cubed. So this is the form of the particular solution that we have obtained after using the method of variation of parameters. And now you can form the general solution y equals to yc plus yp. Yc is c1x squared plus c2x squared ln x, whereas yp is x cubed. Okay, so I've already shown you some examples of how to solve homogeneous and non-homogeneous Cauchy-Euler equation. So that's the end of the lesson in chapter 4.5, Cauchy-Euler equation. Thank you very much.